Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about statistical significance. In hypothesis testing, we declare that a result is statistically significant if the p-value computed from the data is very small. We typically compare the p-value to a certain threshold called the significance level, which is often set at 5%. If the p-value is below 5%, we declare that we reject the null hypothesis, we have a positive finding. Well, if we do this, we're guaranteed that the probability of a false positive is actually bounded by 5%. It's bounded by that significance level. In fact, the whole hypothesis testing framework is set up so that this is the case, so that we are guaranteed to control false positives. This might not be immediately obvious when you first look at the definition of p-values. In this video, we're going to explain why this is the case. Let's get to it. We're going to talk about statistical significance, and to begin, let's remind ourselves of the different steps when we perform hypothesis testing. First, we determine a conjecture of interest. Then we come up with a null hypothesis that contradicts this conjecture of interest, because we take a devil's advocate perspective where we're trying to explain the data as if the conjecture did not hold. We choose a test statistic which should be large if the null hypothesis does not hold. In that case, this would be evidence in favor of our conjecture. We decide on a significance level alpha. Very often it's set at 5%. Then we gather the data and compute the test statistic. We compute the p-value associated to the test statistic. And if the p-value is smaller or equal to alpha, to this significance level, we reject the null hypothesis, which is evidence in favor of our original conjecture. In the previous video, we used this framework to analyze Giannis Antetokounmpo's free throws in the 2021 NBA Finals. Here, the conjecture was that the free throw percentage was higher at home than away, and the null hypothesis was that the percentage is actually the same. Our test statistic was the difference between the free throw percentage at home and away during those finals. And the significance level was set to 5%. So this is the distribution of the test statistic under the null hypothesis. We saw that under certain assumptions, it was Gaussian with a certain standard deviation. And the p-value associated to the observed test statistic, which is here, is equal to 0.011 because that's the probability that the test statistic under the null hypothesis is greater or equal to that value. In this case, this is below the significance threshold, 0.05, or the significance level, so we reject the null hypothesis. What can go wrong? What can go wrong when we perform hypothesis testing? Well, there's two kinds of errors that we can make. The first kind is a false positive. This occurs when the null hypothesis actually holds, but we reject it. The reason why this is called a false positive is that when we reject the null hypothesis, this is like declaring a positive finding. The type 2 errors are false negatives, where the null hypothesis actually does not hold, but we do not reject it. And as I said in the introduction, the hypothesis testing framework is built so that we have very precise guarantees about false positives. In particular, if we follow all of these steps, then we're guaranteed that the probability of a false positive will be smaller or equal to the significance level. This is not immediately obvious. We're going to prove that this is the case. In order to do that, we're going to be in the setup of parametric testing. So we're going to assume that the distribution of the test statistic depends on a certain parameter that we call theta. We're going to, at first, concentrate on simple null hypothesis, where the simple null hypothesis is that theta is equal to a specific value, theta null. In the case of Giannis's free throws, this would be that the percentage at home and away is the same. Okay, that would be our simple null hypothesis. The test statistic under the null hypothesis is going to be called T null. Okay, And the p-value function is defined as the probability that the test statistic under the null hypothesis is greater or equal to any possible value of the test statistic. And we usually evaluate this at the data to compute the actual p-value. The reason why it's important for us to think about the p-value function is going to become apparent in a moment. But now let's take a look actually at the p-value function for Giannis Antetokounmpo's free throws in order to understand what this object is. The p-value function tells us the p-value associated with every possible value of the test statistic. So here the test statistic, for example, is equal to this value, then the probability that we observe that value or a greater value is approximately 0.15, let's say. The data is here. For the data, the p-value is actually 0.01. Okay, so hopefully it's clear that this is just a deterministic value, a deterministic function once we have fixed a test and a distribution for the test statistic that maps every possible value of the test statistic to the corresponding p-value, the probability that the test statistic under the null hypothesis is greater or equal to that value. Okay, here I could have used straight lines, but yeah, it is what it is. Okay, but hopefully you understand that this is a deterministic function. You will see in a moment why this is very important. So now we're going to analyze false positives. When does a false positive happen? A false positive happens if the null hypothesis holds and we reject the null hypothesis, which means that the p-value is smaller or equal to alpha. Okay, so now in order to derive the probability of a false positive, we want the probability that the p-value is smaller than alpha under the null hypothesis. And remember that our null hypothesis is that theta is equal to theta null. So when theta is equal to theta null, what is the probability that the p-value is more or equal to alpha? This requires understanding the distribution of the p-value when the null hypothesis holds. What does that even mean? Well, what is the p-value? The p-value is what we obtain when we plug in the test statistic into the p-value function. The p-value under the null hypothesis is what we obtain when we plug in the test statistic under the null hypothesis, which has a certain distribution, into the p-value function. That gives us a random variable because the test statistic under the null hypothesis is a random variable. So if we plug it into a deterministic function, we get another random variable. And this random variable is going to represent the behavior of the p-value when the null hypothesis holds. In particular, the probability that that random variable is smaller or equal to alpha is the probability of a false positive, because when the p-value is smaller or equal to alpha, we reject the null hypothesis. And here we're seeing what is the probability of that happening if the null hypothesis actually holds. So just to be very clear, as I said a moment ago, the p-value function is a deterministic function. So we can plug in here. Now I'm going to draw straight lines that they look a bit nicer. So, for every value of the test statistic, it's going to map it to the corresponding probability that the test statistic is greater or equal to that value, okay, which is the p-value. So now if the test statistic has a certain distribution, let's say that the distribution of the test statistic under the null hypothesis is a Gaussian, it's a terrible picture, let me try again. It's kind of Gaussian here, and it is approximately Gaussian, right? Like we already, we derived this in the video on the two sample test for Giannis Antetokounmpo's free throws. Then basically what's going to happen, we're going to see under the null hypothesis, we're going to see more values around here, which means that we're going to see like the corresponding p-values are going to be around here, right? Well, it's not immediately obvious what distribution this value is going to have, the p-value, corresponding to what distribution we're going to get for the p-value when we plug in the test statistic under the null hypothesis. But that is exactly what we're saying, right? So on the x-axis, we're going to plug in the distribution of the test statistic as if we were sampling the test statistic under the null hypothesis. And what we're asking is, what is the distribution that we see here on the y-axis after we have mapped the test statistic through the p-value function, okay? This has ended up looking a little bit messy. Hopefully that was helpful to understand what we're doing. Okay, so now we want to derive the distribution of the p-value under the null hypothesis. What happens when we plug in the test statistic under the null hypothesis into the p-value function? The p-value function is a deterministic function that looks like this. Okay, it's a probability that the test statistic under the null hypothesis is greater or equal to a certain value t. Now I want you to think of this guy as just h of t. Don't think about the fact that it has something to do with the test statistic, although that is going to be very important. Now we can write this function as 1 minus the CDF of the test statistic under the null hypothesis. But again, we're just thinking about it as a deterministic function. So because it's a deterministic function, we can plug in, as I said earlier, we can plug in the test statistic to get a new random variable, because the test statistic under the null hypothesis is a random variable. We plug it into this deterministic function, we get a new random variable. That new random variable is what we're interested in. We can write it as 1 minus the test statistic plugged into its own CDF. Again, I can completely understand this being quite confusing, but you have to be very strict about this. You have to think of the CDF as just some function that goes from 0 to 1, which is fixed and deterministic. And you have to think about this guy as a random variable that is being plugged into that function. So hopefully it's obvious that it's clear that then we get a random variable out of this. This begs the question, what happens if we plug a random variable into its own CDF? And you might not remember this, but we already talked exactly about this. We talked about this when we were talking about how to derive the distribution of random variables when we pass them through a deterministic function. And we actually talked about the specific case where you were plugging a random variable into its own CDF. And I told you that this would be important to analyze p-values, but you have probably forgotten about it, so let's review it. Okay, so the idea here is that we're taking a random variable. Specifically, we're interested in when this is the test statistic under the null hypothesis, but the proof is general, and we're plugging it into its own CDF. We're going to assume that the CDF is invertible, but this argument can be easily extended to the case where the CDF is not invertible. So now we want the distribution of B, which is what we obtain when we plug A into this function. B is obviously between 0 and 1 because CDFs take values between 0 and 1. How do we characterize the distribution of a random variable? We often start with the CDF because it has a very easy interpretation, a very intuitive interpretation in terms of a probability. What's the CDF at a certain constant? Well, it's the probability that the random variable is more or equal to that constant. Now we plug in the value of the random variable, or rather the expression of the random variable in terms of the random variable A. And now here we would love to have this just in terms of A, not of A plugged into the CDF. In order to do that, we're going to use the fact that we're assuming that if the CDF has an inverse. This, the event that the CDF is more than B is equivalent to okay, let me draw a picture here. So here what we're saying is we have A, and we have f of A minus 1 B, okay? And a CDF goes from 0 to 1 and is monotonic. So the event that A is smaller or equal, so A is smaller or equal to the inverse of the CDF applied to B, is exactly equivalent to saying that, let me use another color here, saying that f of A is smaller than B because the CDF is monotonically increasing, okay, or non-decreasing at least. So these two events are the same. So this is great because now we have an event in terms of just A. By definition, what is the probability that A is smaller or equal to a certain value? It's just the CDF of A evaluated at that value. Now we evaluate the CDF of A at this value, which we just interpret as a constant. It's very important to abstract yourself from the fact that we are actually manipulating the CDF there. And now what happens? Well, we have an expression where we're applying the CDF to its inverse. What do we get? We just get B. So the CDF of this new random variable B obtained by plugging A into its own CDF is equal to B between 0 and 1. So what is its PDF? The PDF is equal to 1 between 0 and 1. So this is just a uniform distribution between 0 and 1. When we plug in a random variable into its own CDF, things get normalized so that the distribution of what comes out is just uniform between 0 and 1. If you remember though, the p-value was equal to 1 minus the CDF of the test statistic after plugging in the test statistic. So we're actually interested in 1 minus b when b is uniform. Intuitively, if you think about it, this should also be uniform, but let's prove it. What is the CDF of C? The probability that C is smaller or equal to a certain constant. We plug in 1 minus b there. So now we get the probability of 1 minus b being smaller or equal to that constant. This is just the probability that b is greater than 1 minus c. Because b, the CDF of b is the CDF of a uniform random variable, this is going to be 1 minus the CDF of b at 1 minus c, which is just 1 minus c. So this is just going to be equal to, oh, actually, I don't know why I wrote that again. This is just going to be equal to c. So this random variable c, which is 1 minus a uniform random variable, is also a uniform random variable between 0 and 1. We have just proved that the p-value, which is obtained by plugging the test statistic under the null hypothesis into the p-value function, since it has this form where it's 1 minus the CDF of the test statistic evaluated at the test statistic, this has a uniform distribution between 0 and 1. And this is a crucial property of the hypothesis testing framework. I cannot overstate how important this is because the whole framework is set up so that this happens. We also will find it very useful to analyze multiple testing in one of the following videos. Okay, so the CDF of the p-value looks like this, which is great because now you can ask what is the probability that the p-value is below 0.05? Well, it's exactly 0.05. What's the probability that it's below 0.2? It's exactly 0.2. So this means that we can threshold using a significance threshold and ensure that we control false positives. Let's make this very clear. When do we incur a false positive? We incur a false positive when the p-value is below the significance threshold if the null hypothesis holds. But what is the distribution of the p-value under the null hypothesis? It's uniform. So that probability is exactly equal to alpha. This guarantees that the probability that we incur a false positive is actually alpha. We have done the proof for continuous test statistics, but sometimes test statistics are discrete. This is the case in our example with the die rolls, where we had this conjecture that the probability of rolling a 3 was greater than 1 over 6. Our null hypothesis was that the probability of rolling a 3 was actually 1 over 6. And the test statistic was the number of 3s, so it's discrete. Remember that the distribution of the test statistic under the null hypothesis was binomial with parameters n equals to 100 and theta equals to 1 over 6. The significance level here was set to also 0.05, and if you remember, we did not reject the null hypothesis. So a very similar argument as the one that we have just used to analyze the p-value when the test statistic is continuous would yield that for discrete test statistics, the CDF of the p-value is actually bounded by u. So a picture I think is more helpful. Well, let's look at the picture and then we'll come back to this. The picture looks like this, basically. We can show in a very similar way to how we did for the continuous test statistic that if you look at the probability that u is below, let's say 0.5, it's, the CDF always stays below this diagonal line, which means that the probability of being below 0.05 is below 0.05. Okay, so the probability, so this happens for discrete test statistics, and this means that the probability of incurring in a false positive, which is the probability that the p-value is smaller or equal to alpha, is bounded by alpha. Okay, so here it's not exactly equal as in the case of continuous test statistics, because this is a staircase as opposed to be exactly on the diagonal, but we still have the bound. We're still guaranteed for discrete test statistics that the probability of a p-value is bounded by the significance level. Finally, you might be wondering about composite null hypothesis, where the null hypothesis is that the parameter is within a set as opposed to equal to a specific value. Let's remind ourselves that in such cases, we define the p-value as the supremum of over all the probabilities that the test statistic is greater than that value. Okay, where the supremum is taken over the possible values of theta that are within the set associated to the null hypothesis. Well, in this case, we can define this p-value function here, which is how we had defined our p-value function for the simple test statistic in order to apply the result that we derived for simple test statistics. We have to realize that a false positive can only happen if theta is within the set associated to the null hypothesis. So theta is equal to some theta sub 0 that is within that set, and the p-value is smaller or equal to alpha. Okay, so now let's try to bound the probability of a false positive. A false positive occurs if the p-value function, when we plug in the test statistic, is smaller or equal to alpha. We have defined the p-value function for this composite hypothesis as the supremum over all the thetas in this set. Okay, and now the probability that the supremum is smaller or equal to alpha is actually smaller or equal to the probability that for that specific theta 0, the p-value is smaller or equal to alpha. You can see this easily because basically if this happens, then this happens for sure, but the converse is not true. So this event is contained within this event. Now we have the probability that a p-value function associated to a specific alpha, a specific theta. I think I said alpha there. I meant theta. I hope I said that clearly. The probability that the p-value associated to that particular theta sub 0 is smaller or equal to alpha when we plug in the corresponding test statistic. So this falls under the proof that we have just done, where this would be 1 minus the CDF plugging it in the test statistic under the null hypothesis for theta 0, and our result shows that this is bounded by alpha. So this also works out for composite null hypothesis. So what have we learned? We have learned that the p-value has a uniform distribution under the null hypothesis. The first time that you see it, it sounds kind of weird, but this is a very powerful way of visualizing the results from hypothesis testing, which we will exploit when we're talking about multiple testing. And very important consequence, a critical consequence, is that when we threshold the p-value in order to decide whether to reject the null hypothesis, we are guaranteed that the probability of a false positive is going to be bounded by the significance level. And that's all I got. Thank you very much.